Okay, so here we're looking at the last part of trig that we're going to do in this class. And we're looking at what are called complementary angles, as you can see. Now, these are just angles that add up to, so I was recording. So these are just angles that add up to 90 degrees, or if they're both in radians, they add up to pi over 2 radians. That's all they are by definition, and they have to be positive. Again, that's just by definition. So it's two positive angles are considered complements or complementary angles, positive angles, if they add up to 90 degrees, or if they're both in radians, they add up to pi over 2 radians. Again, that's just a definition. So for instance, if you look at 30 degrees and 60 degrees, right? They're complementary, they're complements of each other. If you add 60 and 30 degrees, you get 90 degrees, and they're both positive. We also have 80 degrees and 10 degrees. You know, those are also complements of each other. And in fact, if you take any angle theta that's positive, I know I didn't write down that this should be positive, but again, it's in the definition. The complement of it is 90 degrees minus theta, if theta is in degrees. So the angle theta here has to be both positive and less than 90 degrees. I didn't write that down, but for any angle though, its complement is this, if theta is in degrees. And also, from the definition, this angle theta has to be positive and less than 90 degrees. If it's greater than 90 degrees, then it can't have a complement. That's just immediate from the definition. If instead theta is in radians, then its complement, again, theta is positive and less than pi over 2 radians, its complement will be this. Okay, again, that is just the definition, okay? Just the definition. All right. Now, you might be thinking, well, why do we even care about this? Well, because of these properties, these identities, excuse me. So here what we're saying is if you do, this is saying here, if you do sine of an angle and cosine of its complement, you're going to get the same value back. If you do sine of an angle and cosine of the complement, you're going to get the same number. Same idea over here. Cosine of 1, sine of the complement, you get back the same answer. Now, same thing with tangent and cotangent, right? You do tangent of 1, cotangent of the complement, you get the same answer. Same thing with secant and cosecant. You get back the same answer. In fact, we kind of saw that earlier when we were dealing with 30 degrees and 60 degrees. If you actually look at those values, you'll actually see that sine of 30 equals cosine of 60, and cosine of 30 equals sine of 60 degrees. In fact, the prefix co, that's not just there for decoration, so to say. It's actually there to remind you of this property. Sine, cosine, tan, cotangent, secant, cosecant. We also saw this with when theta, the angle, was 45 degrees. 45 degrees is its own complement, so to say. Complements itself. And sine of 45 degrees and cosine of 45 degrees, they're the same. We saw that earlier. And this is just a reminder that if theta here was in radians and 90 degrees is replaced by pi over 2, then the identities here still hold. So we're not going to do too much with this. Again, this is what that prefix co means. And just a quick example. I don't think the book even goes too much into this. But if you do cotangent of 30 degrees, tangent of 60 degrees, you get the same thing. You get the same thing. Same thing with secant and cosecant. And there's just a quick example. If you know, for instance, tangent of 35 degrees, you can easily get cotangent of 55 degrees. 35 degrees and 55 degrees, they're complements of each other. Hence, tangent of tangent of 35 degrees and cotangent of 55 degrees have to equal each other. So, it's just a quick example I wanted to do. If you actually think about the definition of the trig functions, so back on this slide, with the right triangle and opposite hypotenuse and all that, it's actually not hard to see why these are true. Mostly because the two remaining angles, the one besides the one that's 90 degrees. But I don't want to get too much into it because I figured you guys can do that if you want. But it's really just from unfolding the definitions. That's all it boils down to. I just figured it'd be good to mention this stuff. So now there's only so much we can really do unless we generalize trig functions to angles beyond a right triangle, beyond those found in a right triangle. So for theta, beyond 0 and 90 degrees. Again, that's pre-calc and we don't have time for that. Are there any questions on this? Okay, so these were actually in the notes that I gave last time. So what I'm going to do now is look at the notes I just sent you. Let me go get to those. Gotta stop sharing this. Close this. Okay. I don't know why it's asking me to save. I didn't change anything, but let's see. Oh, there it is. Here we go. All right. So now what we're going to look at is section P5 actually. Okay. Oh wait, that's not the. Okay, that's what I sent you guys. I don't want that. I want the. Oh, here they are. There we go. Sorry, my mistake. I had opened the notes I sent you. So it's not quite the same notes as I have. So I'm going to get to that right now. There we go. Sorry about that. All right. Here we go. So now we are looking at what are called rational expressions. This is actually section P5, so we're jumping back and forth a bit. So we're done with trig, but we're looking at rational expressions. And these are actually formed, as you'll see, from polynomials. If you remember, actually, we saw rational numbers, and you get rational numbers, they're just fractions of integers. So you can get rational numbers by forming a fraction of integers, or if you want, dividing an integer by a non-zero. It's similar with rational expressions, except instead of integers, we use polynomials. In other words, we'll see what a rational expression is, but it's really just one polynomial divided by another. So, just like what we do with integers and rational numbers, you can go from the set of integers to the set of rational numbers. It's similar here. You can go from polynomials to the set of rational expressions, basically by just dividing or forming fractions, so to say. In this case, we'll have fractions of polynomials. Now, just like with fractions of integers, rational numbers, we can multiply and we can divide. We can multiply and divide them. We can do the same thing with rational expression. And in fact, you'll see the procedure is actually the same. So you'll see what I mean. And not today. We'll see how to add and subtract them. That's a little bit tricky. It's not terrible, but just like with fractions of integers, you do have to get a common denominator, okay? You do have to get a common denominator. Okay? Just want to check to make sure I had enough for today, but I do. Okay, so I said what a rational expression is. I actually defined it already, but here's the definition. It's just a quotient of one polynomial over another. Again, just think about the rational numbers, right? What exactly is a rational number? Well, it's the quotient of one integer divided by another one. So, same idea here. So it's a quotient in this form, where P and Q are polynomials. Let me just stop the recording.